Molecules. So many of them in their infinite and beautiful variety, but while that variety is great, it can also be pretty dang overwhelming. And so, in order to help this complicated chemical world make a little more sense, we classify and we categorize. It's our nature as humans, and it's extremely useful. One of the most important of those classifications is whether a molecule is polar or nonpolar. It's a kind of symmetry, not just of the molecule, but of the charge. It's pretty easy to see when you're just looking at them. You got polar and nonpolar, polar, nonpolar, polar, nonpolar. I'm gonna take sides right now. I'm on team polar. I think polar molecules are way more interesting despite their wonky, off-balance selves. Nonpolar molecules are useful and their symmetry has a kind of beauty, but polar, in my humble opinion, is where it's at. Alright, now here are two very different types of chemicals. Right here I have a stick of butter, and then in this bowl, that's just normal water. So I'm just gonna go ahead and squeeze this butter, which if you're wondering is both a terrible and wonderful feeling. And then I'm going to just drop that. Now I'm going to attempt to wash that butter off my hand, but that is just not it's not going anywhere ever. Ever. It's just beating up on me. Why? Because water is a polar molecule and the various chemicals that make up butter are nonpolar, and water wants nothing to do with that. Ugh. So, what makes a molecule polar? Well, two things. First, asymmetrical electron distribution around the molecule. You can't have a polar molecule made up entirely of the same element because those atoms will all have the same electronegativity, and thus the electron distribution would be completely symmetrical. Electronegativity is usually thought of as how much an element wants electrons around it, but I think it's more about how much electrons want to be near that element. If electrons were 13-year-old girls, fluorine would be Niall Horan. They'll do anything just to be near it. Why? Some simple periodic trends. Electronegativity increases from left to right because there are more protons in the atoms, and more protons means more boys in the band. Meanwhile, it decreases as you move from top to bottom because as the crowd of electrons gets bigger, they start to shield each other from the effects of the protons. What I'm trying to say is that electrons are hipsters. If a bunch of other electrons are into that thing, they're less interested. Now, there are a number of other factors here, but just like the relationship between tweens and their latest boy band fixation, it's complicated and weird, and you probably don't want to think too much about it. That chemists label the molecule polar. The result is a partially negative charge on the more electronegative part of the molecule and a partially positive charge on the less electronegative side. The requirement for polarity, you've got to have geometrical asymmetry. CO2 here has the charge asymmetry locked up, but because the molecule is linear in a straight line, it's a kind of symmetrical asymmetry. The same thing goes for CH4 with its tetrahedron of weakly electronegative hydrogens around a more strongly electronegative carbon. These molecules have polar bonds, but the molecules themselves are not polar because the symmetry of the bonds cancels out the asymmetry of the charges. I've heard that like dissolves like, so the easiest way to figure out if a liquid is polar or nonpolar is just to dump it in some water. But the why of this phenomenon is usually just totally glossed over. What's actually happening to those molecules? It seems like they're all just bigots, terrified of anything even a little bit different than themselves. But this is chemistry, so there must be some fundamental reason, and if it's fundamental, it probably has something to do with decreasing the energy of the system. And indeed it does. Those partial positive and partial negative charges of water, they're at their lowest energy state when they're lining up together, positive to negative, into a kind of liquid crystal. There's an arrangement there. It flows, of course, but the oxygen sides are always doing their best to orient themselves toward the hydrogen sides of other molecules. You can even see the effects of that attraction as the surface tension that allows me to pour more than 100 milliliters of water into a 100 ml container. The strength of that surface tension depends on the intermolecular forces that pull molecules of a liquid together. These attractive, also called cohesive forces, pull the surface molecules inward. And what you see when you look at this pile of water is the result of those cohesive forces, minimized surface area in the water in this beaker. When you put a bit of oil into that mix, the water totally freaks out. Oils have notoriously nonpolar molecules, so suddenly there's this mess of uncharged gunk interfering with the nice orderly arrangement of polar water molecules. But if you take a closer look, the processes are very similar to those between water and air. Water does everything it can to minimize its surface area and kind of expels the oil droplets. Rather than the water disliking the oil, it actually just likes itself much more, so it won't mix with the oil. Now if you put polar stuff in, water's all about that, and those polar water molecules just go after whatever other partial charges they can find. Or, in the case of many ionic solids, the partial negative charges on the oxygen side all gang up on the positive ions, while the partial positives on the hydrogen side surround the negative ions, breaking the crystals apart and dissolving them into freely moving ions. In some cases, we can actually witness these interactions in unexpected ways. Mix 50 milliliters of water with 50 mils of alcohol, and what the heck, there's less than 100 mils of liquid. The arrangement of water mixed with alcohol is actually more structured and thus more dense, resulting in a smaller volume. Brings me to one little last polarity tidbit, the hybrid molecule. There are lots of molecules, like the surfactants in soap, for example, that have both polar and nonpolar areas. Dish soap is thus able to dissolve the fatty parts of my butter catastrophe here, and then stick the polar sides out, allowing the whole mess to get washed away by Avogadro's numbers of polar water molecules that I'm sticking on my hand right now. Oh yeah, that's better, but not, I'm gonna have to go to the bathroom to get this all the way fixed up, so be right back. Likewise, the fatty acids that make up your cell membranes have polar heads, which keeps them interacting with the aqueous environment of our bodies, but nonpolar tails, which prevent the cells from just being dissolved by the water around them. Pretty dang elegant, if you ask me.